Thanks. Thanks to Chiache, this project Opaque is something that's been going on since I think 2017 or so. It's also joint work with Wenting, who's in the back. We're both grad students in the lab. The motivation for this project is that companies today collect a large amount of sensitive data, often too much data to process on site. And so the industry has moved to an outsourced model where analytics and machine learning are done in the cloud. But of course, outsourcing computation poses these new security and regulatory challenges. So the current best practice in the industry is to encrypt data at rest and also in transit. But the data still has to be decrypted when it's in use. And that actually poses a major threat that Opaque is trying to address. So let me be more specific about the kinds of attacks that we're concerned with. We're concerned with attackers that might have privileged access to the compute infrastructure that handles sensitive data. These might be external attackers that break into a network and exfiltrate data, or they might be internal attackers, like administrators. And so in this project, we just assume that all systems in your data center could potentially be compromised. And so that red box is indicating the whole cloud is treated as untrusted. For example, there was a recent story in Bloomberg, this allegation of these cloud servers being compromised by a chip added during manufacturing. And that chip is thought to compromise the baseboard management controller, which can read and write memory and can send network packets. So with that capability, you can theoretically exfiltrate your data while it's in use. Now, of course, there's a lot of doubt about that particular allegation, but technically, this actually seems totally possible. So the question we're trying to address is how to protect data from a powerful attacker while still preserving the functionality of our systems. We don't want to compromise that. And one class of approaches that has been present in academia is these cryptographic approaches. So there's a technique called fully homomorphic encryption that you might have heard of. And this lets you compute directly on encrypted data with strong security. And it can theoretically express any computation. But the main problem with this is that it's just very slow. It's way too slow to be practical, more than 1 million x overhead. So there have been, after that, systems like CryptDB that sort of weaken these security guarantees. And they provide what's called partially homomorphic encryption. And that's something that's more practical. It performs pretty well. But the inherent trade-off is that the crypto schemes that they choose limit the kinds of operations that you can do. So there are things that only let you do like additions and multiplications, for example, or only let you sort or compare, that sort of stuff. These purely cryptographic approaches, kind of both branches of them have significant limitations, but there are recent developments into something called hardware enclaves, which offer full functionality and security with only a small loss in performance. And hardware enclaves provide a hardware-enforced secure execution environment, which lets you run your code securely, even in the presence of a malicious operating system. And they also encrypt the memory space so that the secret data is only accessible from within the enclave. And the hardware also, thereby guarantees that even an attacker with root access can't break in. So Opaque is our secure distributed analytics platform that uses these hardware enclaves to enable secure analytics. And Opaque extends SparkSQL in the middle there with extra SQL operators and rules so that analytical queries can be run securely. And an attacker only sees encrypted data. And Opaque works by modifying actually replacing the execution layer of a SparkSQL so that all of its operators run within enclaves. And the advantage of that is it maintains compatibility with all the existing applications that would use SparkSQL, so SQL queries and the various libraries that built on top. So now I want to give a brief idea of how Opaque works, starting with this bootstrap procedure. So first of all, the setting actually is that you can see there's these two halves of the screen. So on the left, there's this trusted client that's required. So something like your laptop, where you can issue queries and where you're confident that it's not compromised. So we need some kind of root of trust to anchor the system. And then on the right, there is this cluster of remote, untrusted servers that have to have these hardware enclaves. So the way that this system starts itself is that, of course, once the input data is encrypted and uploaded, then the first step is a process called remote attestation. And in this step, the client verifies that the enclaves are genuine. This is just a procedure that enclave providers offer. And so that ensures that they're not just like being fake or simulated enclaves. And then it establishes a secure channel that allows us to load code and data and keys as well from this trusted client to the remote server. And this process of attestation and establishing this channel is like a pretty heavy cryptographic process. It also involves talking to Intel to check that these are like are genuine enclaves. And so it's an expensive thing, but it only needs to happen once. And so it takes a few seconds, but it's not per query. Now the next thing is how to actually run a SQL query. So to do that, there's a lot more involved than just these operators themselves. There's in running any distributed query, there's tasks like query planning, task scheduling, fault tolerance, cluster management, all of these kinds of things that Spark and SparkSQL are responsible for. And so you might be wondering, where do those go on this thing? So for security, we need to put some of these components, particularly query planning, we need those to be verified correct. And so for those like essential components, we place them on the trusted client. Whereas for other things like task scheduling, those don't need to be trusted as long as the actual tasks themselves are trusted. The scheduler could do whatever it wants. So these kinds of tasks, which comprise the bulk of the code in Spark, arguably, are put on the servers. So now when we actually go to run a SQL query, the way it works is that the query is first translated into a DAG of encrypted operators, and this is done by both our code working in conjunction with the procedure that SparkSQL usually would follow, and then that is sent to the scheduler, which runs the corresponding tasks on the enclaves, on the workers. And those workers then tell the enclaves to read the encrypted data, encrypted input data. And that is, also they might perform intermediate computations, calculate partial aggregates, things like that. And then these enclaves would finally combine these partial aggregates to return the results to the client via the secure channel. Okay, so that finishes the summary of how Opaque works. Now, we have run some benchmarks to see how much overhead this encryption and enclave procedure adds. And for this workload, it adds up to 2.3x overhead. So this is a log scale, so that's why these bars all look pretty similar, but queries 2 and 3. And then actually, you can see query 1 here is actually a little faster with Opaque. So that's this 0.47x number. And that's curious, but we think that's because our operators are actually written in C++, so they're running in native code, while even with code generation, SparkSQL emits Java bytecode. So we're guessing that's why. But takeaway is that this is not like a super high overhead operation. And also see our paper from NSDI for a lot more details, including we have this even stronger security mode that we added called oblivious mode that also hides the memory access patterns in addition to the data itself. And that is actually the core of the academic contribution. Of course, one of the most important goals of the RISE Lab is building artifacts and open sourcing our projects. So this is open source on GitHub. And we also have been collaborating with a handful of companies, and I'll talk about one of them, IBM Research. So IBM Research has deployed Opaque in a couple of end-to-end use cases for a project that they have called Rest Assured. And that involves integrating Opaque with these other essential security features like key management and like the various components of attestation. And we're also glad that IBM has contributed some of this code, integration code, back to our open source project. And they have documented this whole deployment in a blog post. So I think this is a good case study. And they also have led an effort to add support for encryption to the Parquet columnar file format. And this is like kind of a spin-off project now, but eventually it'll come back to Opaque support for encrypted Parquet. Okay, so back to Opaque. So the way that we extended SparkSQL makes Opaque really easy to use. You just have to call .encrypted on any data frame, and it'll encrypt it, and then after that, these data frame operators will work as expected. Now there are some limitations. So one of them is that we only support the Scala data frame API. So there's no integration with SQL at the moment. You have to go through the Scala API. You can't use Python, but you'll see that our notebook is set up for Scala this time, so that'll be fine. And then also, we have a limited subset of SQL operators and types, which I have a list on the next slide. And also, there's some version dependencies, so only a certain OS and Spark version is supported at the moment. Okay, so and then here are the operators that we have supported, so just for reference. Okay, so I also want to give a sense of what we're working on now in the research domain. So what we're working on is a new project that builds on Opaque to provide secure federated analytics. And Opaque provides security for one organization, but we're thinking like, what if multiple organizations want to pool data and run analytics across the union of that data, but without sharing their individual contributions, their raw data. So an example might be banks that would like to share customer transactions to refine some kind of credit model or fraud model, but don't want to actually share this sensitive customer transaction data with their competitors. So our new project that we're calling OFQ for Oblivious Federated Queries, it adds a federated query planner that runs across those organizations and then chooses how to split a query across each organization's Opaque clusters. So it's kind of a next level beyond Opaque architecturally. And our early results are showing that this approach provides up to 10x speed up over bringing all the data to one Opaque cluster, which you'd otherwise need to do. Okay, so that finishes this talk. Next, we have a tutorial showing how easy Opaque is to use, and you'll also get to see those encrypted operators in the plan for yourself, and also look at the encrypted data in memory, kind of simulating an attacker. Okay, and also you can check out our project, maybe star it if you'd like to. Okay, thanks. I think I can take questions. If I'm not sure what the...
I don't yet see an Opaque link in the Rise Camp tutorials page.
Yeah, so hopefully that link will be made visible. But if not, you can just get it by hacking the URL by putting /camp/opaque at the end of the URL. Yeah, hopefully this will get turned on though.
So if I wanted to run Opaque in different environment, like in other labs, I think you mentioned in one of the slides some of the requirements, but are those the comprehensive requirements, or like some Intel enclave requirements are also there? I mean, there is a dependency on some of those or not? You can run it on any platform.
So sorry, can you say that again? So you're asking about the platform dependencies and whether
yeah,
that's...
to run this Opaque environment or replicate this in the lab?
And so you're asking whether those ones listed are the full set of requirements? Yeah, I think so. So let me go back to this slide, actually. Let's see. Yeah, so I think that the main one is this platform, so the Ubuntu, and that's actually not because of us. It's because of the SGX SDK from Intel that we're using. They only support that platform, actually, I'm not quite sure if that's true, but we've only tested it on that platform. Yeah, the Spark version, and then also, of course, there's just the presence of this SGX SDK and the hardware itself. So while this will work if you don't have the SGX hardware, it'll not actually be secure. So for that, you have to get these servers. I think actually most servers, if I understand, do come with this. But yeah. And also, this runs in Docker and stuff, as we are using for the tutorial.